So we are going to start our next talk on a new addressing mode. Remember, by now we have been using plenty of new instructions. So far we know 4 different addressing modes, right? The immediate, direct, extended, and inherent. Now there are some additional addressing modes we have not covered until now, but this is probably a good time to talk about a new addressing mode, which is called relative addressing. Okay. Now before we talk about the addressing mode, let's first show you an example that why we need a new addressing mode, or how do you run into a new addressing mode. Now let's see a couple of lines of code with a branch instruction. We are familiar with branch, right? We know how the branch works. So if you look at these instructions, in the first line we are loading a data into accumulator A. In the second line we are adding another data to it, right, into accumulator A. In the third line we have a branch instructions. A fourth line we are replacing the data into A, but if the branch doesn't make, then we go to fourth line, right? And then the last line ends the line. Now think about this couple of lines here. We always should be able to write the object code for every line, right? What the object code means. The object code is actually like a machine code. Basically, whatever the code you are writing, the object code is the direct translation of those code into machine bytes, right? Like the binary bits. So we write everything in hex, but in machine everything is written in binary. Remember, in the very first, when we started this class, we learned about the object code, right? Basically we we learned how to convert these lines into the raw machine bits, right? Meaning the binary bits. We actually wrote those in hex, but it's still binary. Now, if you really try to write the object code for these lines, what happens? Look at the very first line. What is the addressing mode? Immediate, right? We know how to write the object code. Second line, still immediate. How about the third line? The third line is something that's really interesting because it's not immediate. It doesn't look like it's direct or extended, and obviously it's not inherent because it's more than 1 byte, right? So what is it? This is where the relative addressing comes into the picture. So every instruction with a branching in it, like this one, is called relative addressing because this belongs to the relative addressing, meaning all the branch instructions, no matter what it is, these are called relative addressing. Okay. Now, why we need relative addressing and how it is written, we'll talk about this very soon. Okay. Now, for every lines of instruction, we can definitely write an object code, right? So, and if you compile your program, remember we compile, and then after we compile, we get a list file, right? And we can always open the list file, and inside the list file, you have already seen that we have the object code for every single line of instruction with all the addresses, meaning where the program is located. You pretty much can tell all of those from the list file. Similarly, if you write something like this, meaning anything with the branches, you will also see an object code. So today we'll try to actually understand how that object code is generated for instructions like where we have the branches, meaning the relative addressing. So again, the object code for every relative addressing instructions like the branch instructions are always 2 byte each, no matter what branch it is. It will be always 2 byte. Okay, remember the object code, some of the object codes are 3 bytes, some of the object codes are 2 byte, sometimes it's 1 byte, but in case of the relative addressing is always 2 byte. Now what are these 2 byte? The first byte is the opcode. Where do I get the opcode? If I go to my instruction set, that is located in the column 5. For every instruction, if you go to instruction set, column 5, we have an opcode. And we already have used it when we actually wrote the object code. Now remember the other addressing mode. What do? You write the opcode, and then in the second position, meaning the next bytes, you actually write the operand, right? The operand that you have in the instruction. But the problem is, In case of the branch instruction, there is no operand. Because in the second part of the instruction, you actually have a label, right? Remember? In every branch instruction, you always have a label in the second part. So that is something catchy. So we don't have any operand which we can write in the object code. So that means that the second byte is something that we need to calculate. And that is always calculated by your program. And we'll also learn how to calculate it. That is called relative address. And the relative address is always 1 byte. Because this is not a real address. Remember, all the addresses which are real addresses are 2 byte, right? So the relative address is something which is like a difference of address. You can probably guess by the name. The relative, right? This is a difference. It's like an offset. Okay, now, so basically, what I'm saying is, relative address will actually be coming from this label here. So we are going to write the relative address for that label. Because think about the label. This is not an operand, right? And it's just a label which actually is a reference to a different line in your program, right? So that is really interesting to see how we actually can calculate an address for that. So this time I wrote the same lines of code here, and the left side I wrote the addresses of these lines which are given to us. Now remember, I think we already know it, right? That every line has an address which is actually the address of the real memory location where the lines are located, right? And I also calculated from there, right? Because think about the first line, the object code of the first line will be 2 byte, right? So that's why you just, the 2 bytes are D010 and D011. So next line will automatically start from D012. Again, that is 2 byte. So that will be D012 and D013. Next line starts from D014. And we know that every line with the relative addressing is always 2 byte. So we know that, of course, the next line will be starting from D016, which is again 2 byte. Okay? Because if you write the object code, you'll know why it is 2 byte, right? We know how to write it. So I wrote those addresses, and I started from D010 just randomly. I'm saying don't think that, okay, I got D010 from somewhere. I was just assuming, it's D010. Now, from here, we'll try to calculate the relative addressing, okay? Now, to calculate the relative addressing, we need 2 pieces of information. Number 1, we need to know where the branch instruction is located. So the branch instruction is actually located here. Right? This is the line where you have the branch instruction. So we will call this line source line. So this is where you have the branch, okay? Now, we are also given the address of that line, right? And we'll call another line a destination line where we have that label, right? Remember? Because this is actually the destination of the branch if the branch makes, right? I'm not saying the branch will make. I'm not saying branch will not make. It doesn't matter whether the branch will make or not. This is the destination. That means if the branch makes, it will branch here. If it doesn't make, doesn't matter, because this is the line which it is referring, right? So this is the destination line. Now, again, as I said, we are trying to calculate the relative addressing, right? So we'll do a little bit of math. To calculate the relative addressing, we need, again, these 2 pieces of information. So the address of the source line, which is called source address, which is, I got from here, right, D014. Address of the destination line, which is destination address, again I got from here, which is D018. These are the only 2 pieces of information I need from the code, and I got it from here, okay? Now, the next step is I will plug it into a formula, which is a very simple formula. If you look at the formula here, this is my formula, RA equals to DA minus PC. Now, this RA stands for relative address. DA stands for destination address. PC stands for program counter. Do you remember there is a register called program counter? We actually have talked about this register because this is a register which is actually controlled by the microprocessor, and this register always holds the address of the next line to be executed. You cannot control it because the microprocessor automatically controls it based on your sequence of programming, but We need this information here. But for now, this is actually easy because to calculate the relative addressing, we actually need the destination address. We also need the program counter, right? Meaning the content of the program counter. This is how we can find it. As you have seen in the last slide, we already know the destination address, right? The only thing that we don't know is the PC. But to find the PC is also easy because to find the PC, we use a very small formula, which is source address plus 0002. It will be always 0002. Okay? We know the source address, right? If I go back, we already know the source address. We know the destination address, which is pretty straight now. Okay? Now remember, before we start the calculation, relative address is always 1 byte because this is not a real address. Let me show you how you calculate it from here. So I have so this is what I'm given. I know my source address, which is given, right? I also know my destination address, which is given. Now to calculate the relative address, I need destination address, which is already given. I also need program counter, right? The content of the program counter, but I can calculate it from the source address. So here you go. I just wrote the formula PC equals to source address plus 0002. My source address is already given to me, right? So I just added 2 with that. That's my PC. So the next step is I plug everything into my relative address formula. So destination address minus PC. Destination address I was given directly, and the PC I just calculated in the last line, right? I subtracted. Very simple. I got the relative address. Now remember, as I said, the relative address is always 1 byte. But as you can see here, this is 2 byte. So how do I fix it? So what I do is I always drop the higher byte. I always drop the higher byte. So basically, I'll end up having only 02, and that is my relative address. But there is a little precaution. You will always drop the higher byte, but remember, the higher byte must be 00 or FF. It cannot be something else. Remember the higher byte that I just dropped was 00, right? Which is fine. And the higher byte also can be FF. Now you might be thinking, what happens if I have a different higher byte than 00 or FF? If you have it, that means your relative address is illegal. So you have to just say, okay, the relative address I calculated and this is illegal. So your answer is actually illegal. Okay? So basically relative address has some restrictions. All right. Let's take a look at everything that we have learned about the relative addressing so far. I have a small formula that I always use to find the relative address. In this formula, I have 3 variables: relative address, destination address, and program counter. Just just like our basic math, if you have a formula in which you have 3 unknowns, how do you solve it? To solve this, you at least have to know 2 out of 3, right? So basically, if you have to find the relative address from this formula, you need to know the destination address and program counter. But in some cases, you probably have to calculate the destination address, given that you know the relative address and the program counter. Because as long as you know 2 out of these 3, you can always find the third one, right? Because in PAWS, in some questions, instead of finding the relative address, we try to find the destination address, given that we know the relative address already, given in the question. So if you have this formula and if you are given a problem, we always, in the first step, we try to find out what variables, meaning the unknowns, we are given. Again, we will be always given 2 out of 3, so we have to find the third one. The step 2, most of the cases you will be already given the source address. From the source address, you can always calculate the program counter, right? Just add 2. Very simple. And then, if the relative address is not given, you can always find the relative address using the destination address and PC. But if your relative address is given, that means you probably have to find the destination address, right? Because you will be given at least 2 out of 3, not all of it, right? So this is the catchy part. If you are given the relative address is always given as 1 byte, because that's how it is written, right? But when you plug it into the formula, you actually have to plug it as 2 byte. So how do you get the other byte? This is how I get it. Whenever I'm given a relative address, I just look at the relative address. If the address is positive, we can always tell the number whether it's positive or negative, right? If the relative address is positive, I put a higher byte as 00. If the relative address is negative, my higher byte would be FF. Very simple. And I can always tell which is positive and which one is negative, right? Just by looking at the hex number. And then I plug the known variables into the formula to find the unknown. So look at a couple of examples to understand it better, okay? Any question up to this point? Let's try some example. Now, we have a couple of examples. The first couple of examples are like plain English example, where you are given the information in the plain English, and then we'll find the information and plug it into the formula and find the solution. Now for an example here, the opcode of a branch instruction is located at the address 0051. That means this is my source address, right? Opcode of a branch instruction, that's my source. And the destination of the branch is 0063. So as you can guess, this is my destination address. Very simple. Compute the relative address that would cause a branch. Now remember, don't get confused. This doesn't mean that the branch will make. Doesn't matter branch will make or not. We always assume that there is a destination address, there is a source address, and we should be able to calculate the relative addressing. Okay? Now, we always calculate it, and if we find that this is illegal, we type ILL in pause, just to make sure we know that the address cannot be calculated, it's illegal. Now, for this example, here is what we are given. We know that the source address is 0051, right? We are also given the destination address 0053, and we have to find the relative addressing. To calculate it, we first find the PC, right? This is what are given in the question. So to find the PC, we plug it into the formula, meaning the source address plus 0002, right? So source address is already given to us. We added the source and 2. We got 0053, and then we plugged everything back to the formula of the relative addressing. Then it becomes destination address minus PC, which is 0010. And again, don't forget we drop the higher byte. So my answer is actually just 10 in hex. And that is my relative address. It's a very simple calculation. Okay? Any question? Let me show you another example, because we pretty much have a similar example, okay? Now, in this example, let's say, think about what we are given. A branch instruction is located at this address. That means this is your source address. Remember, we just need 2 pieces of information: source, destination, or source and relative address. And we find the third one, right? Now here, the source address is given to us, right? Which is 0135, that is given. And we are also given the relative address. See, the relative address is given as D2. But this time, since the source and relative address is given, we have to find the destination address. Remember, as I said, we have 3 variables in the question, 3 unknowns. So you'll be given any 2 out of 3, and you have to find the third one. Okay? Now let's look at what we are given. We are given the source address, which is 0135. We are also given the relative address, which is D2. But remember, we always extend the relative address to 2 byte, right? How do I fill the higher byte? I just check the relative address. If it is a negative number, I fill the higher byte by FF. If it is a positive number, I fill the higher byte by 00. Now D2 is a negative number, right? So I fill the higher byte by FF. I have to do it before I plug it into the formula. Now, what is unknown? Destination address. So I always find the PC because I always have to find it. So PC I can just find from the source address, right? Which is given to me, which is source plus 2. My source is 0135, which is given. I just added 2, which makes it 0137. Now this is my formula to calculate the relative address. But remember, this time we are not trying to find the relative address, we are actually trying to find the destination address, right? So to do that, we'll tweak the formula a little bit. How do I tweak it? I'll try to isolate the destination address, right? Because that is what I'm trying to find. To isolate the destination address, I'll be adding PC both sides. So the PC will get cancelled at the right side, right? If you add PC, those both sides, right? So you will have PC at the left side. So basically, that means the destination address equals the relative address plus PC, right? It's the same formula. I just just tweaked it a little bit. So my destination address. So now I already know my relative address, right? Because which was given in the question, I just extended, right? So I just found the PC here, right? PC I just got from here. You see here the PC I got, which is 10137. So I plugged both into the formula. I added, and remember all the addresses must be written in 2 bytes, right? Because the destination is a real address. Source address, destination address, these are the real addresses. Relative address is not a real address, it's just a difference of address. So my answer is 0109. Remember, if you have a carry, you will drop it. Meaning if you have a carry at the very end, because you always have to write it in 2 bytes. Address cannot be longer than 2 bytes, right? Any question here? Let's try another example. Now again, a pretty similar example. I have a branch instruction which is located at 0300. So that means 0030 is my source address, right? Where the branch is located. And the destination address is also given as 0010. And we have to calculate the relative address. Let's try to calculate it. So we are given the source address, which is 0300, destination address 0100, something 0010, these are given, right? We have to calculate the relative address. So we first calculate the PC, right? We always do it. To calculate the PC, that is source address plus 0002. So the source address is 0300 and then 0002. Once we calculate it, I have 0302, right, as my PC. Now I plugged everything back to my formula to calculate the relative address, right? I already know the destination address and I just got my PC from the last equation. So I plugged everything here and this is what I got as a subtraction. I'm saying after we did the difference, okay? And I dropped the higher byte and I got 0E, but here is the catch. Even if I got the higher byte, I dropped the higher byte and I got the relative address as 0E, this is illegal. Why? Look at the higher byte. That is FD, right? Do you see the higher byte? Anytime if you have a higher byte which is not 00 or not FF, your answer would be illegal. ILL in pause. That means relative address has some restriction. You cannot calculate the relative address for every single types of things. So basically, in such cases, even if you got an answer, your actual answer would be ILL, because the higher byte is not FF or not 00. It cannot be anything else. Any question? So let's try something else like this. For an example, I'm given, let's say, a bunch of lines. So far, every single problem we tried, we are given information in plain English, right? Now we are given information in code. So here I have some bunch of instructions. On the left side, I have, at the very left column, I have the address of those instructions. In the next columns, I have the object code. So these are the 2 bytes of object code for the corresponding line, right? Next 2 bytes of object code. Now here I have a branch instructions in this line, right? Do you see this branch, BRA here? Now that means this is the line where your relative address will come right into picture. See, we gave a question mark here. So that means this is the place where you need to put the relative address. How do I get the relative address? I have to calculate it. How do I get this 20? I got from my instruction set, right? Because remember, the first byte of the object code I get from the column 5, right? I got it from there. But the second byte, which is marked as question mark, is the relative address that I need to calculate. Okay? How can I calculate it? I need to find two different things that is given, right? Source address and destination address. What is my source address? Source address is actually the address of the line where the branch is located, right? Now this is my line where you have the branch. So my source address is given to me as 0040. And of course my destination is also given. Think about the destination. This is the label, right? Destination address, destination line will always start with the label, right? That label. Destination address is also given to me as 004B, right? So we just got those addresses from the code. The rest is just calculation, right? Now this is what would be my calculation. I'm given the source address as 0040 from the code, right? I'm given the destination address also from the code 004B. Can I calculate the relative address? Of course I can. So first step is to find the PC, right? Which is source plus 0002. The source address is 0040 and then I added 0002. That makes it 0042. And then I plugged everything back to my formula to calculate the relative addressing. Same way, right? Destination minus PC. Destination is given the relative address, which is 0009, but remember we have to drop the higher byte, right? Once you drop the higher byte, it becomes 09. Now that means that this question mark byte will actually be replaced by something calculated, okay, which is 09 and a single byte, which will be placed in place of question mark, right? So that will be the byte there, and that is the relative address. Any question?
Yes.
Of course.
So when I look at 9 versus 09, the most significant is the
See, that your calculator will not show you the zeros. Calculator never shows the zero in front of it, because we are just talking about the calculation in your microprocessor, in the bytes. But the computer calculator will never show you the zeros at the front.
Okay, so it is a problem.
But you have to write 09. Because think about this. In the calculator you see the numbers, right? But in this case, in our case, we want to know what will be the byte. So you actually have to fill the whole byte. Because in case of this calculation, calculator will never show you 0009. It will always show you just 9. Okay? Because the calculator is not designed to show you the content of the register, right? It just is doing the binary or hex or other subtractions or additions, right?
So
Any,
if the answer, like let's say it came out 1009,
then it will be illegal.
the,
It will be illegal because the higher byte is not 00 or not FF. If the higher byte is something else than 00 or FF, your answer would be illegal. It can be FF in some cases, right? Depends. Remember when we talked about the branching first time, we talked about there are two different kinds of branching, like positive branching, negative branching. The negative branching is the one which actually branches backward. So in case of negative branching, you will actually run into a relative address which is negative. In case of positive branching like this is a positive branching. You see here, because your branch instruction here you are branching forward, right? So that is a positive branching. That's why your relative address is positive. If you are branching backward, it will always be negative. So basically, I would say if you are running a loop, we have not talked about the loop yet, but just based on the branching, you can guess that the loop is sort of a branching where you go back, right? You will go backward. So where it will be always like a negative branching. and your relative address will always be a negative number. All right, so I'll stop this presentation here. So we only have 2 quizzes for this part. Again, this is a new addressing mode, but we definitely want to understand it. Okay, we'll also need it for some future reference, as you have seen, everything we are learning is somewhere needed to understand the next topics, right? So I'll stop our presentation here so that we can try the quizzes.